Time travel is one of those ideas that seems almost innocent when spoken aloud. A simple rearrangement of words suggesting a clever machine and a daring journey. Yet the moment we attempt to take it seriously, the idea becomes deeply unsettling, because to ask whether time travel is possible is not merely to speculate about future technology, but to confront the deepest foundations of reality itself, to question whether the universe permits logical contradictions, whether cause and effect are negotiable, and whether existence can endure the rewriting of its own history without tearing itself apart. And for much of human history, time was assumed to be absolute, an invisible river flowing at the same rate for everyone, everywhere, independent of motion, gravity, or observation, a universal ticking clock against which all events were measured. Until the early 20th century, when Einstein shattered this comforting illusion by revealing that time is not separate from space but fused with it, woven together into a four-dimensional fabric known as spacetime, a dynamic structure that bends, stretches, and warps in the presence of mass and energy. And this discovery did far more than revolutionize physics, because hidden within it was a quiet but astonishing implication, one that would haunt physicists for generations, namely that if space-time can curve under the influence of gravity, then in principle it might curve so extremely that it folds back on itself, forming loops in time, mathematical pathways known as closed time-like curves, solutions to Einstein's equations, in which an object could, at least on paper, travel into its own past, returning to an earlier moment in its own history. And at first glance this seems to suggest something extraordinary, that the laws of general relativity do not explicitly forbid time travel, that the universe itself appears to tolerate. The possibility of revisiting yesterday, yet mathematics alone does not determine what can physically exist, because equations describe possibilities, not guarantees, and physical reality is governed not only by geometry, but by consistency, by causality, and by the stability of natural law. And it is precisely here that the seductive idea of time travel begins to unravel, because the moment we imagine traveling into the past, we collide with paradoxes that strike at the very heart of logic, paradoxes in which effects eliminate their own causes, where actions undermine the conditions that made those actions possible in the first place. And these paradoxes are not mere philosophical curiosities or clever thought experiments, but existential threats to physics itself, because a universe that allows contradictions cannot support reliable laws, and without laws, prediction collapses, explanation dissolves, and science loses its meaning. And so the true question shifts, becoming not whether time travel is conceivable, but whether the universe is willing to tolerate inconsistency. And every indication we have suggests that it is not, because when we examine the physical mechanisms that might allow time travel, such as traversable wormholes, rapidly rotating cosmic structures, or extreme gravitational configurations near black holes, we discover that nature responds not with cooperation, but with resistance, instability, and catastrophic breakdown, as though reality itself were enforcing a rule that cannot be violated, a principle often referred to as chronology protection, the idea that the laws of physics conspire to prevent travel into the past, not by issuing a direct ban, but by ensuring that any attempt to do so destroys itself before succeeding. And this protection becomes most evident when quantum mechanics is introduced into curved space-time, because the quantum vacuum is not truly empty, but alive with restless activity, particles and antiparticles constantly flickering into existence and annihilating one another. And near a region where time loops would begin to form, these quantum fluctuations are no longer tame, but grow without limit, becoming infinitely amplified, causing energy densities to diverge toward infinity, destabilizing space-time itself, and triggering violent destructive feedback that would obliterate the very structure of any hypothetical time machine, meaning that the closer one comes to violating causality, the more violently the universe reacts, not unlike a physical system pushed toward an impossible state. And this behavior strongly suggests that time travel is not merely difficult, but fundamentally unstable, that the universe possesses built-in safeguards designed to protect itself from logical collapse, And this conclusion is reinforced by thermodynamics, which introduces the arrow of time, the observation that entropy, a measure of disorder, tends to increase, giving time its irreversible direction. And although the fundamental equations governing particles may be time-symmetric, the collective behavior of large systems is not, because reversing entropy would require an unimaginably precise rearrangement of every particle in the universe, effectively demanding a miracle of cosmic proportions. And any genuine form of backward time travel would therefore require not just moving through time, but reversing entropy itself, undoing every interaction, restoring every broken symmetry, unshattering every shattered glass, and reassembling every dispersed atom exactly as it once was, a process so statistically improbable that it transcends mere difficulty and approaches impossibility. And when we combine this thermodynamic irreversibility with quantum instability, a coherent picture emerges, one in which time travel to the past is not explicitly forbidden by a single law, but rendered physically unattainable by the combined weight of multiple principles acting together, while time travel to the future remains not only possible but unavoidable, because relativity has already demonstrated that time flows at different rates depending on speed and gravity, allowing astronauts, satellites, and subatomic particles to leap forward in time simply by moving fast or existing near massive objects. And this asymmetry is crucial because it reveals that time possesses a direction aligned with entropy, memory, and causation, and any attempt to reverse it would require the universe to betray its own statistical foundations. And yet, despite these overwhelming barriers, the idea of time travel refuses to disappear, not because it is realistic, but because time itself remains deeply mysterious. Because even now we do not fully understand why time flows forward, why we remember the past but not the future, or why the present moment feels uniquely real. And this mystery tempts us to believe that time might be more flexible than it appears, that perhaps the past could be revisited or altered. Yet, when we search for evidence of such flexibility, we find none, and the absence of time travelers from the future is itself a powerful clue. Because if backward time travel were possible, even rarely, the probability of visitors, anomalies, or detectable signatures would be overwhelming. And the silence we observe is not an accident, but a fulfilled prediction, evidence that chronology protection operates with extraordinary efficiency. And this enforcement may be necessary not only to prevent paradox, but to preserve the integrity of physical law itself, because laws that permit their own violation cannot remain laws for long. And so the secret rule that stops time travel is not a single equation or prohibit, etched into the universe, but a convergence of principles, relativity shaping spacetime, quantum mechanics destabilizing causality violations, thermodynamics enforcing irreversibility, and causality demanding logical consistency, all aligned toward one outcome: the preservation of a universe capable of existing without contradiction. And this realization reframes time travel not as a technological challenge awaiting future innovation, but as a cosmological impossibility rooted in the structure of reality itself, not because we lack the intelligence to build a machine, but because existence cannot survive the consequences. And yet this does not diminish the wonder of time, because time remains one of the most extraordinary features of the cosmos, a dimension that shapes existence, consciousness, and meaning. And even if we can never step backward into yesterday, our understanding of time continues to deepen, revealing that the present is not a universal now, but a local experience, that simultaneity is relative, that past and future coexist within space-time as part of a four-dimensional structure, and that our perception of flowing time may be an emergent phenomenon arising from entropy and consciousness, rather than a fundamental property of the universe. And this leads to a profound implication, namely that the impossibility of time travel is not a limitation imposed upon us, but a requirement for meaning itself, because if the past could be changed at will, then choices would lose significance, responsibility would dissolve, and history would become endlessly malleable. And it is precisely because the past is fixed that the present matters, because actions cannot be undone and consequences cannot be erased. And perhaps this is the deepest lesson hidden within the question of time travel, that the universe has chosen consistency over possibility, coherence over fantasy, and in doing so has preserved the conditions necessary for memory, understanding, and existence. And so while time travel will continue to inspire stories, equations, and dreams, the evidence suggests that the universe has already made its decision, allowing us to observe time, to measure it, to stretch it, and to move forward within it, but never to reach back and rewrite what has already occurred, ensuring that the story of the cosmos once written remains internally consistent, intelligible, and ultimately knowable. And in that sense, the true secret rule that stops time travel is not an obstacle placed in our way, but the very foundation upon which reality itself stands.